Hey guys, welcome back. Today we're going to be talking about solutions. So this is a pretty important concept to get down just because for the rest of whatever future you have in chemistry or any science, you're going to have to know how to make solutions and you're going to have to know how to use them to calculate different values for compounds. So what's the definition of a solution? It's a homogeneous mixture of two or more pure substances. So what do we mean by homogeneous? We mean that it's evenly mixed. So it's present in equal amounts throughout the entirety of the solution. Now, these solutions are composed of a solvent and a solute. The solvent is the thing that does the dissolving. And it's present in the largest amount. Now, the solute, on the other hand, is the thing being dissolved. And it makes up a smaller portion of the solution. So now that we have that covered, it's important to not mix these up. So say we're talking about salt water. It's composed primarily in this case of H2O and NaCl, so water and sodium chloride. In this case, sodium chloride is not the most prominent part of the solution, it's the water. So water is the solvent, and NaCl is the solute. It's the thing being dissolved by the solvent. So what is dissociation? It literally refers to dissolving. So when the components of the solute are pulled apart by the solvent in their individual components, they are being dissociated. They are dissociating. So say again, in our saltwater example, if we were to take NaCl and put it into water, the water molecules are going to pull apart the sodium and the chloride ions into their respective components inside of the water. This right here is the dissociation. They're being pulled apart. So how does this factor into the concept of electrolytes and non-electrolytes? So electrolytes are ions. They're charged when they split up. So an example of this is, in fact, NaCl, which breaks into Na plus Cl minus when it's introduced into an aqueous solution or into water. So in contrast, non-electrolytes, they dissolve, but they don't dissolve into ions. It means that they interact with the solvent in such a way that they can still be pulled apart from being in clumps. An example of this would be if you put a molecule or a group of molecules into water and it's pulled apart. So here, a prime example would be glucose or sucrose. And for those of you who don't just know what sucrose is, this is table sugar, the regular sugar that you would put into coffee or into tea or on your cereal even. And when you put this in water, it dissolves, but it does not make ions. It's not charged, and it remains in its molecular compound form. So say if it was just glucose, we'd get individual units. of C6H12O6. If it was sucrose, it would be the same here with, I believe, C12H22O11 for this one. Either way, it dissolves. So there's conditions for dissociation occur within this solution. And this primary condition is that the intermolecular forces between the solvent and the solute must be greater than those between solute particles and solvent particles. So what does this mean? This means that with our NaCl example, there is an interaction going on here. This is a force between the ions which keeps them together. It's an ionic compound. And in order to break this apart, our solvent has to be able to overcome this interaction. But in reverse, we also have to keep in mind that, say, if we were using water as our solvent, the same has to happen. If this is in a whole bunch of H2O, we have to keep in mind that water will stick to itself. It's a polar molecule. It is charged. It has partial charges on the hydrogens and on the oxygen. So it has its own forces, its own intermolecular forces that keep it together. So not only does it have to overcome the interaction between the sodium and the chloride, it has to also have its own interactions between its molecules overcome by the solvent, by the solute that's being introduced into the solvent. And ultimately, when this happens, the water can pull apart the sodium and the chloride because of its dipole charge corresponding with the positively charged sodium and the negatively charged chloride ions. But keep in mind that no matter what, if something cannot overcome these interactions, if something cannot make sure that the solvent will be pulled apart and the solute will be pulled apart and that they will interact and do these things with one another, then something will not dissociate. And yet again, this is how this forms. We have our negatively charged oxygen, our positively charged hydrogen, partially charged hydrogen, and they're going to interact with the parts of this ionic compound. The sodium is going to lose one of its electrons to the chloride because it's not quite as, it doesn't want to keep it as much. And so the chloride, because it's negatively charged, is going to want to be near the partially charged hydrogens, and then the sodium is going to want to be near the partially charged oxygen, and it's going to pull them apart. And in return, these charged ions will also insert themselves in between all the water molecules and associate with them because, electrostatic attraction is a thing. Now, an important thing to note here is that just because a solute disappears in the solvent does not mean that this was actually a solute-solvent interaction. It wasn't dissociation. Sometimes we can mistake a chemical reaction for dissociation. So how do you tell the difference? Well, a chemical reaction is an irreversible change. It creates something new. Dissociation does not create something new. Everything that was there before is still there. It's just in a different physical form. Dissociation is a physical change. So just make sure that you know the difference and that you're able to tell this difference. Okay, so now when we talk about solutions, we have to be able to talk about a relative amount of solute in the solvent within this mixture. So that's where we talk about the difference between saturated, unsaturated, and supersaturated solutions. Saturated solutions have they have reached the maximum amount of solute that can dissolve within said solvent. They are completely filled with it, and it's just enough that all of it can dissolve and none of it is going to stay as particulate matter in the solution. It still creates that homogeneous mixture. With an unsaturated solution, we haven't yet reached that point of saturation, which means that we haven't yet put enough solute into the solvent that no more solute can dissolve. There's still room to dissolve more solute in it. And then we're talking about supersaturated solutions. This is an interesting one. They are solutions that have too much solute in the solvent, which means that it can't dissolve. Usually, though, when we have a supersaturated solution that doesn't have visible particulate matter in it, it doesn't have a visible solid in it that hasn't been able to dissociate, it means that it was heated up first, because heating up this solvent enables it to dissolve more solute, and then it was cooled back down. And this usually results in crystallization. It's pretty interesting. I recommend looking up some videos on it. But either way, so we can assign these names, these words, to just generalized pictures. So this first one here is a saturated solution. The second one here obviously has less solute, therefore it's a unsaturated solution. This last one here has a ton of solute in it, which means that it is a super saturated. And if you want a great example of a supersaturated solution and what the crystallization process looks like after it's been supersaturated at a high temperature, think of if you were to take a glass of water, probably not in glass, and you were to heat it up in a pot, and you were to add sugar to it, and you could keep adding sugar until you didn't want to add anymore, or until a point where it will stop dissolving at the temperature that you've chosen. No matter the temperature is still higher than what it would normally be at room temperature where you're trying to dissolve sugar in it. Now, if you take that pot off the stove and you let it cool, as long as you don't disturb it, that sugar will stay dissociated in the water. However, if you put, say, a string tied to a pencil over the pan and just let it sit there, the crystals will attach themselves to the string and they will continue to form. And as more crystals form, it causes more and more of that sugar to come out of solution and to bind to it. And this, guys, is how you make rock candy. You use super saturated solutions to do it. All right, so ultimately, learning about solutions, it has an important place in every part of life, and that is where it comes to molarity. So it's the way of measuring the concentration of a solute in a solvent. In more specific terms, it is the moles of solute per liters of solution. I cannot emphasize this enough. It is not moles of solute per liters of solvent. It is moles of solute per liters of solution, which means that if you have a large volume of solute going into this solvent, that solute still takes up room. It still takes up volume, which means that the liters of solution is different than the liters of solvent. So that's important to remember. Don't confuse them. Don't confuse them. So this is where we're going to apply this now. You've worked on dimensional analysis, converting between moles and grams, and using all of these conversion ratios. So now we're going to start applying it. So if we're told that we have 0.700 mole of glucose and it's combined with water to make a 350 milliliter solution, the concentration of said glucose is what molar? So to start off, we know that molarity is equal to our moles of solute over liters of solution. Now, emphasis on the fact that this is in liters. It's not in milliliters. It's not in microliters. It's not in deciliters. It's in liters. So, important to keep in mind when we go forward. Thankfully here, we are already in moles. We are given the number of moles of glucose. So we can start with our 0.700 mole of C6H12O6. Now we're going to draw our brackets here. And we know that we have 350 milliliters of solution. We are not given the volume of solvent. We are given the volume of solution. And so we can write that down here. We have our 350.0 milliliters of solution, but we can't do this in milliliters because we know that it has to be over liters of solution. Therefore, we're going to convert. So we know that there are 1,000 milliliters in 1 liter. Our milliliters cancel out, and that leaves us able to just calculate across. We're going to multiply 0.700 times 1,000 and then divide by 350, and we happen to get 2.00 molar C6H12O6. And this molar right here, big M equals mole per liter. Anytime you see that, it's an abbreviation for moles per liter. It's just molar. And we kept in mind that we started with 0.700 mole, has 3 significant digits, so our final answer has 3 significant digits. All right, so a slightly different way to come about this. So what is the concentration of a solution in which 98.0 grams of sodium hydroxide is dissolved to give 550.0 milliliters of solution? So this question isn't nearly as nice as the last one. We are given our solute in grams instead of moles, which means keeping in mind that molarity, as we know, equals moles of solute all over liters of solution, that we need to not only take our grams of solute into moles to be able to calculate this, but we also need to get our milliliters of solution into liters to finally calculate the concentration. So how do we start this? We're going to start with our sodium hydroxide. However, in order to get from grams of sodium hydroxide into moles of sodium hydroxide, we have to calculate its molar mass. So how are we going to do that? Well, pull out a periodic table. You guys have practiced this before. Sodium is approximately 22.99 grams per mole, and oxygen is 16.00 grams per mole, and hydrogen is about 1.01 grams per mole. Add these together and we get a whopping 40.00 grams per mole for a molar mass. So now that we have that, we can go ahead and write down our 98.0 grams of NaOH. Draw our brackets. So we know that we have 40.00 grams of NaOH per 1 mole of NaOH. Our grams cancel. So now we're in moles, which is where we want to be. So now we take into account the 550.0 milliliters. So we have 550.0 mils of solution. We know that there are 1,000 milliliters in 1 liter. Our mils cancel, which we're left in moles per liter, which is what we want for molarity. So we go ahead and multiply across. 98.0 times 1,000 divided by 40 times 550, and we get 4.45 molar NaOH. Now, keeping in mind, we started with 3 significant digits with our initial mass of NaOH. We end with 3 significant digits because that was the lowest number for this. All right, guys, if you have any questions, go ahead and ask Mrs. Merriam. I hope that this helped you out some. Solutions are pretty interesting, and I hope that you have fun doing the molarity lab if you guys can. See you later.